Hello everyone, I am Sarbani and I am going to talk on the temperature dependence of Pauli Paramagnetic susceptibility and free electron heat capacity in a generalized d-dimensional space. This is mostly based on the concepts of Pauli Paramagnetism for absolute zero temperature, which can be found in any standard textbook. Here, I will extend the concepts to the case when temperature is non-zero. That is, it takes some finite value. This part is based on a paper by Edmund C. Stoner and is titled Collective Electron-Specific Heat and Spin Paramagnetism in Metals. Lastly, I will speak on a small extension to a generalized d-dimensions. I hope at the end of my presentation you learn something new. So, this is how I have planned to proceed. I will start with the Fermi-Dirac distribution function and move on to the theory of free electrons in metals, followed by the concept of Pauli Paramagnetism. All the three topics will be discussed for the two cases of absolute zero and any finite non-zero temperature. Then I will generalize the concepts to d-dimensions and finally discuss the results. Now let us see how the Fermi-Dirac distribution function is different for the two cases of absolute zero and non-zero temperatures. At 0 Kelvin, all the energy levels up to the Fermi level are filled up. States above the Fermi level are all empty. This situation can very well be described by a step function or a heave-side function. At higher temperatures, the transition between the completely filled states and completely empty states is gradual and not abrupt, as can be seen here. The Fermi-Dirac distribution is given by this expression, where mu is the chemical potential. We can get back the step function simply by putting t equals to 0 here. This deviation from the step function that we see here for a finite non-zero temperature is smaller for a lower temperature value, and the deviation increases as the temperature is increased. The area of the shaded regions on the left and the right sides of the Fermi energy are always equal. This follows from the fact that the area enclosed under a curve describing a probability distribution, also called a probability density function, is always unity. We all know that the dispersion of free electrons at 0 Kelvin is parabolic and that the density of states is proportional to the square root of energy E. The shaded region here represents the filled states. We will now use these concepts discussed so far to explore Pauli Paramagnetism. Pauli Paramagnetism deals with magnetization of free electron gas with two spin states, resulting from spin flip of the electrons in the presence of external magnetic field. In this theory, the contribution from orbital motion of electrons is neglected. Now, what does this mean? We saw in the previous slide that the energy of a system of free electrons is given by this expression, where the energy E is proportional to k squared. This is responsible for the parabolic shape of the dispersion of free electrons. But when an external magnetic field is applied, the expression modifies to these two equations here. As is evident, the two spin states now have different curves to describe their respective dispersion relations. The curve for spin-up electrons is higher in energy than that for spin-down electrons by the same amount. When an external magnetic field is applied, the curve for spin-up electrons move up in energy by an amount mu b times b, where mu b is the Bohr magneton and b is the magnitude of the applied field. But the curve for spin-down electrons shift down by the same amount. Hence, the net difference in the energy described by the minimas of the two curves is twice of mu b times b. Okay, so the top ones are for spin-up electrons and the bottom ones for spin-down. These two graphs on the left here are when there is no external magnetic field. These two on the right are when an external magnetic field is applied. Now for these, we have energy along the x-axis and density of states on the y-axis. So this can be easily obtained from the plots we saw on the previous slide by simply flipping the two axes. Coming back, the spin-up electrons rise up in energy by mu b times b. But the fact that only states up to the Fermi energy can be filled leads to flipping of spins of electrons from up to down. The newly spin-flipped electrons can now be accommodated easily in the empty states created here due to lowering of the energy of spin-down electrons. This results in more number of electrons pointing downwards, and hence magnetization develops in the direction of the applied field. This phenomenon is known as Pauli Paramagnetism. At T equals 0 Kelvin, the magnetization is derived to be proportional to the external magnetic field as we just discussed. The Pauli paramagnetic susceptibility can be found by taking the derivative of magnetization M with respect to H, which is the auxiliary field, and is equal to B by mu naught. Now, we come to the case of non-zero temperatures. The Fermi-Dirac distribution is no longer a step function, but shows deviations. In order to solve for energy, specific heat, etc., we have to solve integrals which have the Fermi-Dirac distribution function multiplied to the integrand. One such example is this integral. This one is for the energy of either of the electron's spins and hence is half of the total energy of the system. This is the Fermi-Dirac distribution function. Integrals of this form can be easily solved using the Sommerfeld expansion. An observation that we should make here is that in the expression for specific heat, we get a linear dependence on T for low non-zero temperatures, since we can neglect the higher order terms. But as the temperature increases, T cube dependence of specific heat becomes dominant. Now, we can generalize the concepts to any random dimension. For this, we follow the same approach as the previous non-zero temperature case with just the expression of density of states generalized to d dimensions. This is the general form where alpha is the proportionality constant. Notice that when d is 3, we get back the square root of E dependence for the 3D case we talked about earlier. These expressions here show a very strange behavior if we put d as 2. The susceptibility is independent of temperature, but the specific heat is not. And this happens only for d equals 2. Notice that the second term of the Pauli paramagnetic susceptibility vanishes when we put d equals 2, and so does all the higher order terms. The only non-vanishing term is the first term, which has no temperature dependence. But the expression for specific heat is linearly proportional to T for all values of d. This is what I found mathematically, but I am not sure if this has some physical consequence. Anyway, we can say that a two-dimensional system can be treated as the only case when we can see temperature-independent spin magnetism. I now summarize my talk into these 3 bullet points. The Fermi-Dirac distribution function is found to have a different nature for finite temperatures, and so does the theory of Pauli paramagnetism. Generalization of the concept of Pauli paramagnetism to d dimensions shows strange consequences when we put d as 2. Thanks for watching. I hope that my presentation was helpful. In case of any questions, please post it in the comments section. If you liked this video, please put a thumbs up and feel free to type in your comments and suggestions. Thank you. Have a nice day.